Bismillahirrahmanirrahim. In the name of Allah, the most beneficent and merciful. Dear student, Assalamu alaikum. My name is Dr. Rana Farhat Mehmood, and today we are back with our lecture 3.5 on single crystal X-ray diffraction. And this single crystal X-ray diffraction is the part of our main course, X-ray diffraction techniques. So this is one of the technique that we studied in this chapter number 3, and the course code of our this X-ray diffraction technique is CAM 5134, and we have studied this course in our second semester of MS chemistry. In this technique we are going to study the neutron diffraction. In the previous lectures, we have studied that we were using X-rays as a source. But in this lecture, we will study about the neutrons scattering or neutron diffraction pattern, or we will take as a neutron as a source instead of X-rays. So what is neutron diffractions? Neutron diffraction is a method by which neutrons are used to determine the atomic and magnetic structure of a material. It can be equally well applied to study crystalline solid, gases, liquids, or amorphous material. Here are some properties of the neutron, and we all are known to these properties. The mass of the neutron is 1.67 10 raised to minus 27 kilogram. Neutron have no charge. The spin is plus half and its magnetic moment is 1.91, and the mean life is 15 minutes. Here is a neutron diffraction schematic diagram in which we are saying that neutron beam is used as a source to strike the crystal or the sample present in its way, and the samples may be a crystal or some other molecule. And we know that the neutrons have some energy, and when it strikes the sample, its energy is changed, and it also diffracted to certain angle, or it is scattered to certain angle, which is recorded on the film, and its diffraction pattern is noted in the recorder. So the detail about this neutron diffraction will be studied in the coming slides. In this slide, firstly we will discuss a brief history of the discovery of neutron, and then we will move on towards its application in the scattering of the crystalline material. Neutrons were first discovered by J. Chadwick in 1932, and after 4 years in 1936, W. Eliezer proposed the idea of neutron scattering by crystalline materials. In 1936, F. Bloch predicted the feasibility of the neutron scattering by magnetic moment in condensed material, and then in 1940s and 1950s, High flux neutron reactor source were built in US and Canada. After that, in 1994, Nobel Prize was awarded for pioneering contribution to the development of neutron scattering technique for studies of condensed matter. Bertram N. and Brockhaus for the development of the neutron spectroscopy, and Clifford G. Scholl for the development of the neutron techniques. So these were the scientists who were awarded as Nobel Prize in 1994 for the development of the neutron scattering techniques. Dear student, in this slide we are going to discuss the principle of neutron diffraction. Neutron incident particles are neutral and scatter exclusively from the nucleus rather than the electron, and that type of scattering is due to the nuclear force. So neutron particle have advantage over the electron particles because neutrons are neutral particles while electrons are negatively charged particles. In neutron diffraction, it is an important probe of investigation of internal structure of a crystal, and it has the potential for providing information which is not possible for XRD and electrons. Here is a diagrammatic representation of neutron diffraction technique in which neutrons are taken as a source in the form of white beam. These neutrons are passed to the monochromator so that it can be a uniform wavelength of the neutron. Then these monochromator wavelength neutron are passed through the monitor, and after this it strikes the sample. The sample direct them to certain angle towards the analyzer, and these neutron are, after passing through the analyzer, reaches the detector. Some portion of the neutrons also goes straight where beam stopper is used to stop the neutrons beams. Dear student, here we will learn about that why neutrons are used for diffraction instead of X-rays and other sources. It is used because the wavelength is comparable with the interatomic spacing. That is, the wavelength of the neutron is comparable with the interatomic spacing of the crystal, and the kinetic energy is also comparable with that of atom present in a solid, and it has penetrating power. Bulk properties are measured by using its penetrating power. Bulk properties of the solid or of the sample are measured by using neutrons diffraction. The weak interaction with matter aids interpretation of scattering data. And the isotopic sensitivity of neutron allows contrast variation, and the neutron magnetic moment couples to B neutron sees unpaired electron spin. Explanation: neutron diffraction is a very expensive technique as compared to X-ray diffraction technique. So in order to get a sufficiently intense source of neutron, a nuclear reactor is needed. Few laboratories have their own neutron facility, and instead experiments are carried out at central laboratories which provide a user service. These are present in different countries like France, UK, and some other countries. In spite of its high cost, neutron diffraction is a valuable technique and can provide information, especially on magnetic materials, that is not attainable with other techniques. Clearly, it is never used when alternative techniques such as XRD can solve a particular problem. So neutron diffraction technique is only used when other techniques fails to solve that problem. Neutron beams are usually of low intensity, and therefore for diffraction experiment the sample size required is relatively large, at least 1 millimeter cubic. Since crystals of this size are often not available, the crystallographic studies are usually carried out on polycrystalline samples. A powder neutron diffraction pattern looks very much like an X-ray pattern, but there are several characteristic differences between the neutron and X-ray diffraction. The first difference is that the neutron obtained from a nuclear reactor give a continuous spectrum of radiation, without the intense characteristic peaks that are present in X-ray spectra, as coming in the following figure in next slide. The neutrons that are used for diffraction, so-called thermal neutrons, whose velocity and therefore wavelength are controlled by the temperature inside the nuclear reactor. These neutrons used for the diffraction have wavelength of the order of 0.5 to 3 angstrom. In order to have monochromatic neutrons for conventional diffraction experiment, it is necessary to select a particular wavelength and filter out the remainder using the crystal monochromator. Most of the available neutron energy is wasted. Therefore, the beam that is used is weak and not particularly monochromatic. So here is a figure that shows X-ray emission spectrum of copper, and the other is showing white radiation that is used by the neutron diffraction. So these are the peaks that we can obtain in the X-ray emission spectrum, in which intensity is taken on y-axis and the wavelength is taken as on x-axis. A recent exciting advance used pulsed neutron source coupled with time of light analysis. The neutrons are obtained using particle accelerator to bombard a heavy metal target with high energy particles such as protons. The efficiency of the suppletion process yield about 30 neutrons per protons. That gives a high neutron flux suitable for diffraction experiments. In the time of flight methods, the entire neutron spectrum of variable wavelength is used as a fixed diffraction angle theta. The neutron wavelength depends on the velocity given by the de Broglie equation, that is lambda is equal to h over mv, where m is the mass of the neutron, that is 1.675 10 raised to the power minus 27 kilogram. Hence, the diffracted radiation arriving at the detector is separated according to its time of flight and wavelength. The fundamental law of diffraction is again Bragg's law, which is n lambda is equal to 2d sine theta. In the time of flight method, lambda and d, that is the spacing between the layers, are the variable at fixed angle theta. This compares with conventional diffraction technique, in which d and theta are the variable at fixed wavelength lambda, and the pulse method gives a rapid data collection. It may therefore also be used for studies of short time phenomena, especially in experiments where samples are subjected to pulsed magnetic fields. And a second difference between the neutron and X-ray diffraction is that the scattering power of atom towards the neutron are completely different from those towards X-rays. In the latter, scattering power is a simple function of atomic number, and light atoms such as hydrogen diffract X-rays only very weakly. While with neutron, the atomic nuclei, rather than extranuclear electrons, are responsible for the scattering, and in fact, hydrogen is a strong scatterer of neutron. So, neutron scattering is very useful for the elements with very low atomic numbers. In addition, since atomic nuclei are effectively point scatterers of neutrons, there is no dependence of neutron scattering power. The so-called neutron scattering length on sine theta over lambda, unlike the form factors for X-ray scattering. This means that the intensity of the powder neutron diffraction pattern does not show the general decrease with increasing Bragg's angle that is seen with powder XRD pattern. There is no simple dependence of the neutron scattering power on atomic number. Also, there is not such a wide range of scattering powers of neutrons across the periodic table as there is for X-ray. This means that heavy atoms in the crystal structure dominate XRD patterns and therefore form the basis of methods such as Patterson's method for structure determination. But it can create difficulties in structure refinement using XRD data if light atoms are present or atoms of a similar atomic numbers that cannot be readily distinguished by XRD. Neutron diffraction, by contrast, is less useful for structure determination because because of the absence of particularly strong neutron scatterers, but it is good for structure refinement using the retrieved method because almost all atoms contribute significantly to neutron scattering. Additionally, some atoms cause a change of phase of pi to lambda by 2 in the diffracted neutron beam and others. Notably, vanadium do not diffract neutron at all. And for this reason, vanadium can are used as sample holder in diffraction experiment because they are transparent to neutrons. Crystal structure determination. In crystal structure determination, neutron diffraction may be used for crystallographic work in cases where XRD is inadequate. It has been much used to locate light atoms, especially hydrogen in hydrates, and organic structures. Usually, the main part of the structure is solved by X-ray method, and neutron diffraction is used to locate the light atoms. Neutron diffraction is also used to distinguish atoms that have similar X-ray scattering powers such as manganese, iron, cobalt, nickel. The neutron scattering powers of these atoms are different and for instance, superlattice phenomena associated with the manganese iron ordering in alloys are readily observed by neutron diffraction. Dear student, in this slide, we will discuss about magnetic structure analysis. The magnetic properties depends on the presence of unpaired electrons, especially in d or f orbitals. Since the neutron possesses a magnetic dipole moment, they interact with the unpaired electrons and consequently these are diffracted by both atomic nuclei and unpaired electrons. This forms the basis of the powerful technique for studying the magnetic structure of material. A simple example of magnetic structure and order is shown by nickel oxide. By XRD technique, nickel oxide has the face-centered cubic rock salt structure. When examined by the neutron diffraction, however, the extra peaks are observed, which indicate the presence of a superstructure. This arises because the unpaired d electron in the Eg orbital are arranged so as to be anti-parallel in alternate layer of nickel atoms. Following figures will show all about this information. Neutrons detect this ordering of spin, whereas X-rays do not. Here is a diagram which is showing antiferromagnetic superstructure in manganese oxide, iron oxide, and nickel oxide, showing pseudo-cubic unit cell for which a supercell that is equal to a subshell oxygen positions are not shown in this figure. The unit cell of antiferromagnetic nickel oxide, which is stable below 250 degrees centigrade, has 8 times the volume of the paramagnetic nickel oxide, and it is stable above 250 degrees centigrade. The structure also shows a slight rhombohedral distortion involving a contraction in the 111 direction perpendicular to the planes of ordered nickel plus 2 ions. This distortion is very small and it is detected by the splitting of reflection such as 111 plane and 111 bar plane in high resolution neutron powder diffraction pattern. For the present purpose, we may ignore this distortion and can treat the structure geometrically as cubic. Neutron powder diffraction pattern for manganese oxide, which behaves very similarly to nickel oxide below and above the Neal temperature Tn, together with a schematic powder X-ray diffraction pattern at room temperature, are shown in the following figure. Comparison of the two patterns above Neal temperature Tn, B and C show that lines appear in the same position but are of very different intensities. Here is a figure which is showing the intensity on y-axis and the angle 2 theta on x-axis. So here is a X-rays display in the bottom, and in the middle neutrons Diffraction pattern is shown at 293 Kelvin, and same for the X-rays, same temperature 293 Kelvin, and in the top there is a neutrons at 80 Kelvin, showing different kind of diffraction pattern for different planes like 111, 311, 222 planes, 400 planes, and 331 planes. So this is the schematic neutron and powder X-ray pattern for manganese oxide for wavelength having equal to 1.542 angstrom. Peaks are assigned as Miller indices for the cubic unit cell given. Neutron data adopted from Schell, Strasser, and Wallin. So this is the reference from this figure is taken. So Physical Review 83. It is an American journal, American Physical Society. So dear student, thank you very much for listening this lecture. This was our lecture number 3.5. That was mostly about the basics of neutron diffraction, and this lecture is still continued, and we will discuss more about this neutron diffraction in the coming lecture number 3.6. Till then, Allah Hafiz.